In this lesson, we are going to look at supervised machine learning algorithms. Specifically, classification type problems, how we can solve classification problems using supervised machine learning algorithms provided with scikit-learn library. To work with this notebook, you have to load several libraries, and there are more submodules, also classes and some functions. For example, NumPy and Pandas, we always use them for data processing work, to process numeric data and the tabular data. We use NumPy and Pandas. And Matplotlib and Seaborn we use for data visualization. Here is how you can load the required classes, submodules, and some functions come with the Matplotlib. We also use scikit-learn library, and it's a tree submodule to do some visualization of tree-based classifiers. As classifier algorithms in this notebook, we are trying to use logistic regression, decision tree classifier, random forest classifier, support vector machines, and k-nearest neighbor classifier. So they're all provided with the scikit-learn library. So this is how you can load the required classes. They all are actually classes. Each model is a class. Then we want to have a function to split our dataset as train and test datasets. So we are using scikit-learn train and test split function. To do the model evaluation, to know how good your models are, so we have to use some metrics. So we use scikit-learn metrics submodule and associated functions within that scikit-learn metrics. In this notebook, we are going to use a famous dataset called iris dataset, which provides us to solve a problem with multi-class classification. In the previous problem we discussed for classification, we solved a binary classifier type problem, which was to predict whether a person earned greater than 50K or not, using the characteristics of that person, such as education, their job type, whether they're married or not, and what is their current living status, etc. So that was a binary classifier problem. We use 1 out of 2 class. So whether the person earned greater than 50K or not, that's a binary classifier. So in this dataset, we are predicting 3 classes. So this iris dataset is like a dataset about flowers and their characteristics. You can find another form of this iris dataset by the flower images you can use for an image classification type of problem. But in this dataset, you have a tabular dataset. Someone collected some characteristics of that flower, such as some measurements of the parts of those flowers. So let's look at the dataset in detail in the coming cells. But if you want to learn more about the dataset and read more about the dataset, you can go to its source, the UCI machine learning repository, and you can also find out the original research article and some other details about this dataset. So I highly encourage you to go to this link and read about the dataset we are going to use. But I will provide necessary details while we are discussing about the data in this notebook. Okay, so this is the dataset location. So before we start any data work, we have to load the data into our computing environment or our workspace. In this case, our notebook. So we are using Pandas library to handle data in this notebook and also for the entire machine learning model building process. So therefore, we have to load the dataset into Pandas data frame. So we use Pandas read_CSV function to load this dataset, which is originally residing as a CSV file. You don't see the CSV extension, but if you look at this file in a web browser or a notepad, you will see it's a comma separated file. You can load CSV files to Pandas using pd.read_CSV. This is a function. You have to provide a file name or file path. So in this dataset, we don't have any headers. So there are no headers. If you looked at the dataset, the dataset is only having values without headers. Therefore, we have to explicitly say to the function we don't have headers. So how you can do that is providing the header parameter as none. And then later we are going to see whether the data is loaded properly. We are using head function to check whether the first 5 rows of the data set. So let's execute this cell and see the output. As we expected, we loaded the data set, we saw the data.head returns us the first 5 rows, and we also knew like there are no headers, so the headers were named as the columns were named as 0, 1, 2, 3, 4 by default, but they are not actual column headers we should have in the data set. So then we need to find out what are those column names. So let's do that next. So assigning column names with any data set, you will be working in machine learning problem or data analysis problem. The data could be coming from your client, data could be coming from your own sources, or maybe internal database or somewhere else. You should have a data description associated with it. So in this data set, we have a data description to say which column is which parameter or which measurement carries in each column in this dataset. Like we already saw, the dataset has 5 different columns. The first 4 columns have some measurements, and the last column is the class of that flower belongs to. Right? We will explore these things in a later time, but you will see those column names. You can also read this document called iris.names that contains some details about the dataset plus definition of each column. So there we can find first 4 columns is sepal length, sepal width, petal length, and petal width, and the last column is class. So we can assign list of column names to the data frame if we know the data frame, how many columns are in this data frame. So we can provide a list of names matching the number of columns in that data frame. So then we can assign it to the attribute. For each data frame, we have attribute called data frame dot columns. So in this case, data is our data frame name or the variable storing the data frame, and the dot columns is the attribute. So we can assign that list of columns. So here we are going to do that. Okay, and then we want to visualize like how our data looks like after we assign column names. And we first of all, like any data set, like we explored multiple times before, we wanted to know the data better. So therefore we wanted to do some preliminary study about the data, such as doing some basic descriptive statistics and finding out how many columns, how many rows are there, etc. So here, soon after assigning the column names, I would like to see the descriptive statistics of this data set. So like we expected, so now the column names were assigned. So we can also do one thing. So this we could do before. We can say data.head after we assign the column name. So you can see the column names were no longer as like 0, 1, 2, 3. So we have proper names, right? So if you do the data.describe, we get the descriptive statistics. I put the parameter include all. That indicates you will get the descriptive statistics for both numeric and non-numeric or categorical data fields, right? You will see the sepal length, sepal width, petal length, and petal width. They are numeric columns. So you can also do one more thing before that. So you can say data.info, so which gives you, that's a function which gives you like detailed information about the data types and how many columns, how many rows are there. So here we knew like 5 columns are in this data set, and to know how many rows, so it will say it will have 150 entries. That means 150 rows, which index start from 0 to 149. Here are the column names, and then their data types, and each column, if they have null values, you will have an indicator saying, okay, so we have 150 entries, but less than 150 non-null values. Here the data set is complete, no null values, therefore you have a full data set. As we expected, we have first 4 columns are floating point numbers, last column is object. We saw it's a string value, which is a categorical value. All right, so let's look at the data descriptions. So the sepal length, sepal width, those four numeric columns we can find the mean value, standard deviation, minimum and maximum value, 50th percentile, or the median value, 25th percentile and 75th percentile, right? So we can find out each and every numeric column. And for the class or the categorical column we find in this data set, we find iris set. We have 3 different unique categories in this data set. That's a useful information for us. We know now 3 different classes we should expect. That confirms what I said earlier. And we know the highest occurrence category is iris setosa is the category. So out of 3, 1 out of the 3 categories. And the frequency, how many samples with this in this category, is 50. So like that we can have like some understanding about the data set after we load. That's why this describe function will be very helpful for you to start with after you loading the data set. All right. So then let's look at some pre-processing steps. So what things you can do in order to make this data set ready for a machine learning related project or a data analysis or dashboard building type of a project. So we have to do some data pre-processing. In most situations, data is not readily available for you to use right away. So you have to do some pre-processing. You may need to transform columns, you need to do some data cleanup, you need to find out some issues and correct them in the data. So we discuss this in detail about when we discuss exploratory data analysis and feature engineering, but let's revisit some of them in this notebook as well. So we have to do checks whether your data exists some duplicates. Duplicates is sometimes going to be a problem in data analysis unless the duplicates are expected. So if the duplicates are existing because of a data entry error, or maybe when you're combining 2 different or multiple different data sets together, they have like some duplicate values exist. Same record may exist in each and every record, or multiple data sets you combine. So therefore they are real duplicates. But in some situations, the duplicate can be in your data set, such as 2 people can have same set of information you collected. In this case, if the scientist looked at 2 different flowers, and they may have same characteristics or same measurements coming, maybe the 2 flowers are identical, but they're coming from 2 different flowers. But we don't know in this case what was the correct reasons. Therefore, and also to help you to understand how we can remove the duplicates for educational purpose. So we will try to remove the duplicate records. So we will make sure our data set has only unique rows. Okay. So first, before we removing duplicates, we need to understand what are the duplicate rows, and how many duplicate rows exist. To do that, we can use the function in data frame. So in the data frame objects called the data is our data frame object, and data.duplicated. So data.duplicated will return a series of true false values. If the record you are looking at in each row is a duplicate row of another, it will say true. If it is not, it will say false. Therefore, if you have 2 records with same characteristics or same values in each row, so the first row will not be considered as a duplicate, as a true for duplicated, and the second row you found out with the same set of values will be considered as a duplicate and flagged as true. Right. If you pass this true false column or true false series into data or square bracket, or you can pass it to data.log to be explicit. So you will get the resulting data set which contains the rows flagged as duplicate rows. So in this case, we found out 2 duplicate rows in this with these values, and one duplicate row with this set of values. So in this case, we have to understand, in this data set we had three rows with the same set of values, right? So therefore 2 made as duplicates, and the last row we should have like 2 different rows with the same set of values, and we found like this is the duplicate, and the original one is, we cannot say original, but the other row is already in the data set flagged as false for duplicated. So now we wanted to remove these rows from our data set. That's what our target. To do that, we say data dot drop duplicates is the function in pandas. So we have the in the pandas data frame, we have drop duplicates function, and we have to instruct keep first. Means it will keep the first occurrence of this row set of duplicated rows and remove the rest of them. You can say the keep last if needed. In place true, we all know this before. We worked with multiple commands using in place before. If you say in place true, it will do the operation you asked to do for the data set or data frame, and it will modify the data frame in memory. So you don't need to assign it back to another variable. It will change the data frame in place. That's what in place does. If you don't do this, it will make the change, but it will not retain the change in the data frame. All right. And then after do this removing the duplicate action, we wanted to see the data description again. So we remove the duplicates, and we found out we actually expected we removing 3 different rows. So we have like 147 rows we removed. Remaining after removing these 3 rows, and we now have the data description for that 147 rows remaining. So then another thing we wanted to note here is we have class names in the class column for each row, and we wanted to find out how many unique classes. I already mentioned to you, you have that information coming from the describe function. If you wanted to get it programmatically in another place, you can use any column name dot unique. So that will give you, or that will return you, how many unique values, or no, the list of unique values in this column, right? If you want to find how many unique values, you have to say n unique. It will return you 3 as the value. So here we know how many unique values, but we don't know what are the unique values. So therefore we wanted to check that. So we call the column name dot unique as a function. It will return us 3 different values, an array with 3 different values. So iris setosa, iris versicolor, iris virginica. So then we have to do one more thing. If you wanted to use a machine learning algorithm such as logistic regression, you need to provide a numeric value as the target variable. So here the class is our target variable, or the type of the flower we are going to predict is our target variable, right? Which is the class column. So if you wanted to convert into numeric value, we have to apply some transformation to that column. So therefore we can we have like 2 different ways. I will introduce the first way for you to understand it better. First way we want to do this is as data class column. We're going to temporarily assign into, not temporarily, so this is the new column we are going to create with the numeric value. So we call it like y_act, means y actual, or the target variable, the actual value of the target variable. We also call it a ground truth, because that was the known result for this row historically, right? So that's what we are using to train a supervised algorithm using supervised method, right? So that's what the known result for this record. So the class we assign temporary, the value actually assigned temporarily to y_act. So it will be the one of these 3 values for each row, and then we are going to replace one by one. If the value is iris setosa, we're going to use 0. We are going to replace this value by 0, numeric value. And then for iris virginica, we're going to replace by 1. Iris versicolor, we're going to replace by 2. So how we come up with 0, 1, 2? That you can also take it random, because there's no rank or inherent order for these flowers. But I chose some method which is like a label by count. So which is having the least count, which category is having the least count, I took the least number, highest count, I took the highest number. Like you can observe this here. If you wanted to see this, you can take the value count. We're going to look at it later time. So you will see the iris versicolor was having the largest number of rows.
Okay, so let's execute this and try to check a sample of 5. The sample function, we already know what it does is it will draw a random sample from your data frame and return you number of rows specified by this parameter. If you don't provide any number, it will return you a random row, one row. If you provide a number, it will return number of rows you provided. Here I wanted to see if randomly pick 5 rows, so you have this here. So just wanted to make sure our transformation is correct. We as we expected, we converted this iris virginica to 1, iris setosa to 0, iris versicolor to 2, right? So this is the way, like step-by-step way you can do this transformation, but you don't need to do the call this replace function, because replace function, what it does is it asks you to provide the original value and the transformed value, or the value you expected to have in the place of this original value, and then in place true will same as the previous command, in place true will change your data frame or apply the operation to your data frame and save it in memory. It will retain. So you can also use the replace function with a dictionary. In this method, so in the replace function, same method, but the way you provide parameters are different. You have to provide replacement dictionary, which you instruct the pandas function, replace function, as a dictionary, which value to replace by which value, right? So in this dictionary, key is the original value, and value in the dictionary is the value you wanted to be replaced into, right? So iris setosa to 0, virginica to 1, and versicolor to 2. So that's what this dictionary. So you can create this dictionary and provide into a replace function. Here you don't need to provide two parameters with the original and the new value. That information is provided within the dictionary. Okay, so that you have to say, but in place is true because you have to apply this operation. So if you execute this, it will give you the same result. You will create a new column called yact, and then it will simply replace the original value in yact by the new values you specified by the dictionary. Okay, so we did this. You can also think of like what are the other pre-processing tasks you can do. We talked about like multiple things we can do. We can explore that in a later time. So we knew from the previous exercises we discussed, for a regression type of problem, like we intended to use logistic regression, you have to take your variables into same scale or apply normalization or scaling techniques, right? So you can apply as z-score like a standardization method, or you can apply min-max scaling method, or any other scaling method that you prefer. So you can use either scikit-learn min-max scaling and scikit-learn standardization functions, or you can create your own functions to that. But in this notebook, we are not going to do the normalization or standardization. We are using these values as it is. All right. So let's do some more steps. We already did this one before to explore the data set. So data.info, like we already knew this. So it will give you the list of column names, how many rows exist, and what are their data types, and also how many non-null values exist. Other information such as the data types, count of data types in this data set, as well as the memory usage you can find under info. The info is a very useful function to know that your data set by the counts and the memory footprint, data types, and identifying whether there are null or missing values in the data set. So keep that in mind. These things you have to do as a habit when you have a data set. You don't just get the data set and try to apply into a machine learning model building step, or don't try to plot it as soon as you read the data set. So you have to have some good conversation with your data, like I always say. So you have to know your data. You have to have some meaningful conversation, ask some questions, and understand what data can tell you before you use this data in your work. Okay, so this is the info is one useful function. Describe is another useful function, will provide a lot of descriptive statistics about your data set. All right, so let's move forward, and we can do some univariate analysis. I already mentioned the descriptive statistics will provide you univariate analysis. And function, another useful function is value counts. It will provide you, given a row, how many values in each category. Given a categorical row, how many counts in each category, right? So we, in the class column, we expected to have 3 different categories, and we now can see how many rows are coming from each category. Like I mentioned earlier, so we know now the iris versicolor is the highest occurring category, and iris virginica is the next, and iris setosa is the next. Okay, and then we can also use this value counts on a numeric columns. You have to apply that meaningfully, you have to provide a parameter called bins. I will demonstrate you here for your understanding, but for this problem we really don't need to use that. So let's try to demonstrate that for the sepal length. And if you wanted to use value counts, I have to say bin. I would say give me 5 bins. So it will divide your numeric range of your data set, or of your column range, into 5 different bins, and then provide the counts for each bin. For example, we know the sepal length minimum value is 4.3 and maximum value is 7.9. So it divided the range into 4 different bins. So you will see they are not in order of the sepal length value, but they are in order of the counts, right? From the highest to lowest. So you will see the least, the right or leftmost bin is 4.29, which is 4.3. You expect to 5.02, and then the next bin is 5.02 to 5.74, like that. So the important thing here is you have to provide the parameter for if you want to apply value counts on a numeric column, which is containing like continuous values. So you can apply that. But if you are applying for categorical column, you can provide as a you can use it as a function without any parameters. It will provide you how many counts coming from each category. Okay. And then let's try to explore some of the data visualization methods. What things you can do with this data set to know this data, and what type of visualization you can make. So first explore how we can plot a pie chart, right? So we all know pie chart. There are some debates about using pie charts in the data visualization. The rule of thumb is if you have like a very large number of categories, you should not use pie chart. Instead, you should use other type of chart such as bar chart. The reason is when pie chart is getting crowded with number of categories, the reader cannot focus on the actual proportion. So there are other types of charts, ring charts, and there are many different charts available, better than pie chart. People recommend, the expert recommend you to use. But pandas library or with matplotlib provide you the function or the capability of drawing pie chart. So here what we wanted to see is visualize the proportion of your data set belong to each category, each flower category in this class, right? So what you need to provide is the data set or the series you take out from this operation, data class dot value counts. So that will give you a frequency table category and how many counts for each category, and then you can directly call the plot function. Have to provide kind is pi, and the auto percentage is auto PCT is a parameter. You have to provide like a format of the number you wanted to display, like here. So 34.0, what it instruct the pandas to do is display the percentage with the 1 decimal point, right? So this 0.1, say the 1 decimal. If you want to display like with 2 decimal points, like 34.15 kind of a thing, so you can have 2 as the decimal point. So this will simply print on top of your pie chart on each section. It will display the percentage to make your plot will tell more information than the proportion you can find in the color regions. Okay, So the bar chart, we already looked at it in a previous notebook. So you can simply plot the bar chart by providing the kind is bar for the plot function. You can also plot histograms for a given column. So this is another univariate analysis. You can do a visual type analysis. So you can say the plot kind is histogram. You can apply the plot function on any column directly now. You don't need to summarize first and apply like a bar chart or pie chart. If you say hist, it will do the histogram or the binning and then finding the relevant bin size, etc. By default, it will give you like 10 bins or less depending on the number of categories you have. So let's see like how we can do the histogram. So here histogram is crowded because I plot everything on one plot. So you can also divide your plot. You can plot in a tile or the grid. Each plot can have individually each column. So you can also do that. So let's look at the kernel density estimation. So here plotting kernel density estimation also in one plot. So you will see how the kernel density estimation for each variable looks like. So since the range of these variables are not very far away, I can easily visualize. But if the ranges are very different, say like one variable is from 0 to 10, another variable from 100,000 to 200,000, you probably will not get a pretty picture or pretty plot in that case. Therefore you have to plot them separately. So we will discuss in a later time how you can use the data visualization part more effectively with pandas, but for now we can use this one. All right, so then let's apply some bivariate analysis. So bivariate, we all already discussed about this topic, involves two variables at a time. So multivariate, we learn about multivariate analysis. You can use multiple variables together at a time. We don't need to go to three variables at a time with this data set, but let's look at two variables at a time. So what are the two variables we are going to look at? We wanted to understand this data with two different columns. So one is the class column and the other column is the each variable. So how the class affecting each variable is what we wanted to see. So here we are going to use again like the data visualization technique. We are going to plot kernel density estimation for sepal length in this first cell we wanted to execute now. We wanted to look at the sepal length for each class. So let's look at them. So we are plotting them together, right? So we can do one modification here. So we can say label. We can say the class is iris versicolor. We have to provide a class, so that will enable the one of the missing piece of this this plot is there's no legend. We don't know what is the green, what is blue, what is orange tells you, right? So that we have to add that, and we have to say legend is true. So let's do the same thing here for the other three curves, right? And then let's make it Virginica, Cetrosa, and then versicolor. Oh, sorry. What did this label? It's a typo. Label. Okay. Let's execute. All right. So now we got the plot as we needed. So we have the variable as x-axis, variable value for each variable value for sepal length, and then the density will tell you what is the density for each of the class, right? So the green curve represent the iris setosa, and the blue iris versicolor, orange is for iris virginica. So we see some separation. So each class is peaked at different values, right? So that's a good indication. So that will tell us there's a dependency of the sepal length with the class, right? So it will be a useful information for us to make a prediction. All right, so let's look at another feature, sepal width. with 3 different classes. I'm not going to do the same modification I did here to add label and legend. You can do in your own time when you are working on this notebook. Okay, so here we don't see much separation between blue and orange, which was iris versicolor and iris virginica, but we have some separation with the iris setosa, the green curve. So let's look at another one, the third one, the petal length. Okay, so that has like a nice separation. Green, which is iris setosa, is peaking at a very low value of the petal length. And then blue is iris versicolor, is having and also the other one is having a peaked at higher value compared to the iris setosa. So let's look at the other one, the petal width. So we have another similar separation, but you can, this is how you can explore your data, and you can try to understand some characteristics of your data set, or some information. You can get some good insights even before you do attempt to do machine learning. So even before you are attempting to do any kind of a dashboard or data visualization or other advanced data analysis methods. So you get from the descriptive statistics, by these visual methods, you will get a good understanding. So therefore, don't ever forget that when you are analyzing data before you are going to machine learning. Okay, so let's try to do the next step we wanted to cover here, finding correlations. To find correlations, if you have a larger data set, we had this issue previously. Correlation matrix will be huge. If you wanted to limit your column set, you can find out how many columns in your data set. You can simply call data.columns, and you can print the list of columns, and then you can select the set of columns you wanted to apply the correlation. So here we have only 5 different columns. We can safely assume we can apply the correlation to entire data set. But here I wanted to limit that and show you how we can do that. So we have to pass data to the square brackets. You need to pass the list of column names, and then you have to call the correlation function, CORR. So that is your correlation function in pandas data frame. So that correlation function applies on your data frame, and then it will find the correlation between each pair of variables, right? So then let's see what it produces. It will produce the correlation matrix, as you already saw this in our previous lessons, right? So you can find correlation between sepal length and sepal width, and also the correlation between sepal length and the actual y-actual value, so which is the class. You already know this, the diagonal of the correlation matrix is always 1, because the correlation of a variable with itself is always 1. So here some observations are, you can notice the correlation between sepal length and y-actual is 0.44. What was the variable having highest correlation with the y-actual is the petal length. So the next one is this is a positive correlation. The petal length and the y-actual is having the positive correlation. Sepal width and the y-actual is having a negative correlation. Remember, but this y-actual does not mean any meaning of the numeric order. So therefore, we need to take this correlation with the y-actual with care. So, but if your class is having inherent order, which is like if your class is the class you're going to predict will tell you something about order, so then you can make a good use of this correlation. But here in this problem we can get good use of correlation for the variables themselves, the x variables or the features themselves, right? So one important observation I wanted to show you here is the petal width and the petal length. You're having very high correlation, is 0.96. Also the sepal length and the petal length having very high correlation, which is 0.87, right? So that those indicate whether when you are doing something to petal width, so there's a high correlation with petal length. So if you are increasing petal width, petal length also getting increased. If you are increasing sepal length, petal length also getting increased, right? So these are like some of the observations you can find out from this correlation matrix. And lastly, you can use the seaborne heat map to visualize the correlation matrix. Okay, and then we can look at, we can, that's another question, we can identify what are the highly correlated features. Okay, so we already discussed about this earlier. So what are the highly correlated features? We can decide if you have like large number of columns, you can decide whether I should drop them or not by looking at this correlation matrix. But now in this data set, I'm not going to drop. I will keep all 4 features regardless of what correlation matrix tells us. Okay. So now I'm going to do another data visualization, apply data visualization technique from seaborne library, which is called pair plot. So let's apply that pair plot and get the output. The pair plot will help you to understand relationship between variable pairs, same as the correlation matrix. Let me take it to the full screen. Okay, so maybe I should zoom out to make it visible. Okay, so the pair plot creates a grid of plots. Each grid point will be a column in your data frame. So same as the correlation matrix, it will tell you the diagonal of this pair plot will tell you the data distribution. If you are having a categorical column, there will be bar charts. If you are having a continuous or numeric columns, you can get the kernel density estimation or histogram to the diagonal, the variable with itself. So that will make no relationship between with other variable, but you can display histogram or kernel density estimation. If this is a categorical or type variable, you can get the bar chart. So in this case, we apply hue as the class, so we will have different colors for each class. So that's why you see blue, orange, and green again in this pair plot. If you don't do this, all curves will be displayed with the same color. And also the off diagonal plots in this grid represent a scatter plot, a relationship between one variable with another. For example, this plot will tell you the relationship between sepal length and sepal width. Okay, so you will also see so how each class looks like, how the data distribution for each class. So you'll see the blue is Iris setosa, and orange is Iris versicolor, and green is Iris virginica. So all the blue, if you take blue alone, you can see you have an increasing trend, which is a positive correlation. But if you take all 3 together, you probably won't have a good correlation for all together, right? But for individual class, you have. So in this case, orange and green, Iris virginica and Iris versicolor, having a good positive correlation, but Iris setosa is unsure from this view. Like that, you can get some idea about how your data is distributed, and also this pair plot itself contains a lot of information, such as the distribution of your column values based on the category, as well as the distribution or the relationship in a scatter plot by the category, right? So you can also see this will also showing some clustering as well based on the category. If you take 2 variables, by the clustering also you can identify which type of flower it is. So these are like some side understandings you will get or insights you get if you do very careful data analysis, right? Probably you don't need to go to advanced machine learning techniques in this problem. So this is a very simple problem actually. That's why we are using it for education purpose everywhere. But even for a real problem as well, you can, if you do a very careful data analysis, you can actually get the best method to solve the problem, or best method to get the result you want, or to build the model, right? Okay, so we do the data visualization, and then we will go forward with our machine learning model building steps for this classification problem. Remember now, if you forget,
we are trying to solve a problem about these flowers. So we have 4 different characteristics. Assume a scientist collected those characteristics for you, and and also the same scientist provided you the class for each characteristic, right? So each flower. So he or she studied 150 flowers and got the measurements to get the first 4 characteristics, and then also give you the class for those each row. So what you want to do is you are trying to build a model to predict that class from a given character. If you provide a new flower, but you don't know which class it belongs to, but you can measure those same characteristics, right? As the previous study does, and then your model should be able to predict which class this flower belongs to, right? So we repeated about these characteristics or features. So these are the 4 features in this data set. We call them like x variables, and then our y variable is y-act. I call it like y-act, so which is your class. Class will be your y variable. Actually, I want to label it as y-act in a later time in this model building step. So if you we already did this earlier. So if you get your feature data set, so you don't have the target variable or y variable in your feature data set. Remember, one mistake you can do without knowing is having your y variable or target variable in the feature data set. So make sure you don't. Therefore, be careful with that, and that can happen. It can happen to me. It happened to me. If you do that, you will see some unbelievable accuracy in your model. It's too good to be true. So therefore, but the model is not trained well, right? So you basically what you are trying to do is you are giving questions and answers to the same student who you want to be evaluated. So that's, make sure you don't do that. So here we have only features, and then why we are taking the y actual as a separate column out. Okay, and then we can again check what are the 3 unique classes after we convert the class labels in string to a numeric value. We did it above. So we have now our class labels are 0, 1, and 2. And the replacement dictionary we already created above. So this is what we use to convert a string value of a class name to a number, right? So we already discussed about this. So but here I just wanted to remind you what we did and what we have in our data set. Okay, so you see 0, you need to understand that this belongs to this class. So to use scikit-learn model, so any model, you have an option now to provide a data frame as your x or feature variables, and a series as your y variable, or column of your data frame is as your y variable. You can also provide, and this is how it was before, you have to convert your data frame into numpy array, 2D numpy array for your feature variables, and 1D numpy array for your y or target variable. Now you don't need to do that. You can directly provide a data frame and a series, but optionally you can do that. So if you execute these 2 lines, so it will convert your data frame into or feature data frame, not without the target column or y column. It will this dot values attribute will provide you an 2D numpy array and assign to x variable as a new numpy array, and y will become 1-dimensional numpy array. So again, you can call like a data frame series out of it, data frame column out of it, and taken as a series. So this will be a series, and then if you call dot values attribute, it will become 1-dimensional numpy array. So you can do that and assign to x and y, and later you can use in the model building process. But here I'm not going to do that. We will use the most convenient way of using the data frame as it is. So here I'm getting the x. I'm creating a variable called x, so that contains the feature data set only, and I call it as x. So let's look at, we already looked at it earlier above, and then we are going to use y as a series. We extract a column which contains a y variable, which is y actual, and we extracted it and we assign it to y
variable y, so that contains a series. So then we need to do the train test split. So I explained this earlier. So you have to do this train test split because you don't wanted to give the same set of questions to student as the daily quizzes and in a class, right? So they will practice with it, or the practice problems. So you are giving some practice problems to students every day. You're having the session, and then you're trying to make that student prepared for the exam. But what if you gave the same set of questions in an exam? What is your goal is by giving an exam is to check the student's knowledge. You wanted to make sure the student learn or not. But if you gave same set of questions you gave for practice in the exam, you don't know whether that the student learn or not. Probably student learned, but there's a chance of being student did not learn anything but memorize things and then answer your test well. So he can make 100 points, but nothing learned, just memorizing your questions and answers, right? Same way, when we are training machine learning model, we should not provide the model the same training data set if we want when we want to evaluate it. So how good our model is. So we have to split our original data set into two parts at least. And then first part we are using for training only, and the second part we are using for testing or evaluation only, to know how good your training or how well your model trained. So that for that purpose we are using the testing data set. You're testing any record from your testing data set should not be part of your training data set, okay, vice versa. So let's try to create a logistic regression model. So first let's execute this scikit-learn train test split function. You have to provide your feature data frame, and then target column, which is a series, and then you have to provide test size. I provide here 20% of my original data set use as the testing data set, and 80% use as the training data set. The random set, you can provide any number, that is you can arbitrarily pick a number, so that will be the seed to generate random seed. Because that I mentioned to you when we're discussing about the sampling techniques. So train test split is deriving a random sample out of your data frame. And we also check after we do the train test split how the data distributions looks like between testing and training data sets. So we saw like they are similar. That's because of the random sampling. Okay, the reason we are using random sampling is to be like well representation of your original data set or the population, and also the samples you picked from this method should also be representative of each and every characteristics as much as possible. So let's execute, and we get the information out of this 147 samples. We get 117 for training and 30 for testing. This is relatively small, not relatively, it's very small sample compared to real world problems you will be solving later. And we already did this the income data set is with some 40,000 plus records, and car miles per gallon problem is with several hundreds of records, right? So you will be doing like more data. We are working with more data sets in future with large number of records. Therefore, this will be very small. So let's solve it, or let's try to create logistic regression model out of it. In scikit-learn, the logistic regression is the class. This is the constructor. So we are going to create the model object in this line. So we are going to create this model and assigning it a variable called model. So the model will now be logistic regression model. Okay, so we can execute. It will create model object, doing nothing but creating the model object. So the next step is what actually doing the task. So it's using our training feature variables and the target variable from the training dataset. So we have to remember this is a supervised machine learning problem. You have to provide features and the target variable or labels. Okay, so features and labels are characteristics of a supervised machine learning problem. Okay, so we previously learned scikit-learn use the function name fit to train your model.
right? So all scikit-learns you will see here down in the notebook, it uses the same function, fit. So model.fit, you have to provide your features and their labels or the target variable column to train. So right, this will simply train your model. Since this is like very small data set and the logistic regression is also a very simple machine learning algorithm, it will be very quick and instantly you will see the model got trained. So you now have the model created and trained and now ready to use actually. So before we use it in the actual application, we have to test it. We have to evaluate how good your model is. So let's do that step by step. So before you do this, and let's do some other few understanding of the model object. So let's access some of the model attributes. So what we know about the model, what we can access from the model. So the model object, you have an attribute called classes underscore, which will return you an array containing a list of or items of class labels as your model C. And also this will be a useful information to know when the model returns certain results. So those results are in the same order. If those results are belong to a class or all three classes, for example, the probability of some for each class. So we will get to know about this in a coming cell in the down of this notebook. But using this attribute we can understand how the model see the classes, which order your model consider classes, right? So that one you can know using this attribute. And then when the logistic regression model fit, so unfortunately I don't have a logistic regression equation on the screen right now, but you can look up logistic regression equation, and you remember the linear regression equation. We use a1 a0 plus a1 x1, a2 plus x3, a3 plus x3, like that. So the feature multiplied by a coefficient, and then add all the features and coefficient multiplied by each individual coefficients together, and then add the intercept value. So that will be a linear regression equation. So logistic regression is also having the exponent value, and you have this coefficient and the feature value plus the intercept in that equation. So how you get the coefficient values for each variable is this. So the model dot coef underscore. Okay, so now you will wonder why we have 3 rows and 4 columns each in this coefficient matrix. Okay, so if you do the same for our binary classifier problem, you probably won't see this. You probably see one row with the number of items equal to number of variables you used in the model. So in this case, we have 3 different classes. What it does internally in logistic regression is it will try to build 3 different models internally. So each model will tell you whether this record belongs to this one class or not. So that method we call one versus all, right? So the first model will tell you whether this record belongs to class number 0 or not. Then the second model will tell you whether this record belongs to class 1 or not. Third model will tell you whether this record belongs to class 2 or not, right? So that the binary classifiers, 3 binary classifiers will help us to build this multi-class classifier, or like ternary, or the classifier with 3 classes. Okay, so this is the first model to predict whether class 0 or not. These are the coefficients. To predict whether class 1 or not, these are the coefficients. Predict whether class 2 or not, these are the coefficients. Okay, so let me zoom in a little bit. All right, so these are the coefficients. To know the intercept for each model, so you will get 3 values because 3 models are being made here. So we have 3 intercept values. Yes, so you can reconstruct the equations using the intercepts and the coefficients, three models, and then you can
can use these values, and you can use it with Excel, or maybe you can code in another programming language. You don't need to use scikit-learn model. You can make your code in your own. That's why the logistic regression will be very helpful if you wanted to create a custom code or use it in Excel. You can get the equation out. It will not be a black box model like many other models we will be using. So you can get the equation very easily and also use that equation easily. Okay, so now we have a list of values, but we don't know the feature names exactly. So if you want to get the feature names as the model identifies it, so these are the feature names, the same order your model identifies it. So how you can get that? You can say model.feature names in. Then we can do the prediction. So now we did some understanding about the model object. So now we can do some predictions. So model.predict proba. So what it does is it will simply give you the model predicted probability for each class. So here the result comes after you run all like in these three models internally, and internally it will provide you one value for each class, right? So not three different models, but it will provide you one value per class, and we will see the predicted probability. Okay, so here also like a two-dimensional numpy array you get. So let's try to understand what it is telling you. So each row belongs to the probabilities for each class for that row, right? The input row value, right? So the say if this belongs to a flower, so you provided four different measurements for that flower, and you provided that to the model, and these are the three probabilities. Tells you how likely this flower belongs to each category, whether it belongs to category 0, 1 or 2. So we have names for each, but let's say 0, 1, 2, 3 are the cover classes. This is 0 is your first column. We saw that in our previous understanding of the model classes, how it identifies. First column is 0. That's why I say this will be important to know the order of classes as your model identifies. 0, 1 and 2 is the order. So anything comes here is 0 class, 1 class and 2 class. So from this one you can find out like which class it belongs to, that flower. Here is 0.0017, right? So it's 1 out of 1000, and here is 5.8. so this focus on this negative e to the power, so not e to the power minus 1 is not e, it's actually 10 to the power minus 1, so 10 to the power minus 3, right? So 1000th, and this is 100th, oh sorry, 1/10th, and then this is actually 5.58, and this is 0.41. So if you were to decide which class this flower belongs to, I hope you understood by now. So you will say it belongs to class 1, class number 1. So 0 class, 1 class and 2 class. The second row we have 0.93, 0.043, 0.043 and 0.024. So it's obvious this flower belongs to class 2, class number 2, right? So 0, first column is 0, second column is 1, third column is 2. All right, so if you wanted to take the predicted value out of it, so what function you should be using? You should use the model.predict. To get the probabilities, you have to use predict underscore proba and provide the testing dataset. Okay, I forgot to mention, for this evaluation you are not going to use training. I mentioned to you, but I have to remind you, you have to use testing dataset. This testing dataset is not a part of your training dataset. Therefore your model did not see these records before, and if your model trained well, the model should be able to predict well on these testing samples as well. So that's what we are trying to check. To get the predicted class directly without the probability, you can use the model.predict and then provide the testing features, and then it will provide. So here but I did the prediction, and then I'm going to take first 5 rows, because this predict function and predict probability function will return numpy array. So what this square brackets and colon 5 does is it will get rows from the beginning to the fifth row, so 0 to 5 index. So first 5 rows, basically this will tell you after you get the predict probability or the predict, give me first 5 rows. So that's what it tells you, right? So that's why you see 5 rows printed here, because it should have like 30 rows in the testing data set. Okay, so these are the predicted classes. Now you can verify whether your first class, whether your guess is correct. So you predicted is first class number 1. Yes, that's correct. Class number 2, that's correct. And the third one is class number 1 as well. It's 0.97 versus 0.0026, 0.014. Both are very small. 97 is the class and this should be the class 1. And the third one is another 97, class 0. The fourth one is class 0, fifth one is class 2 because 0.56 versus 0.42, the next highest one. So this means, and then class 2. So you'll see the predict and predict probability how you can use. So these are the functions. Not only in you can use not only in logistic regression. I am not going to describe in other models. You can use in random forest. You can use the predict function in random forest, tree classifier, support vector machines, and other scikit-learn models as well. Okay, so now let's look at how you can create a result data frame. So now we have a column we provided for the training process from your original data set. We know if for each flower you have in this testing sample, you know the features, you know the target variable, or you know the known class, right? So you know the class of each flower you provided in the testing data set that we call earlier as y actual. So we have the y actual column, and then for each flower in the testing data set for all 30 flowers, you put the features through the model and predicted a class. So now you have two columns. You have the predicted class, you have the actual class column. And then also you run through the predict proba function to get the probability values, and you get the probability values out of it. So here is how actually you can get the probability values for each class. Like we already saw, this model predict probability will return you a two-dimensional array. Your rows will be rows for each flower in this data set, and columns will be for each class. So if you want to isolate a column, so this is how you can get. So if you want to isolate your column, first column, you have to say give me all rows and then comma, but the first column only, and the all rows comma, give me the first index column 1 only, the second column, and then give me all rows comma column index 2, which is the third column, right, which belongs to class 2, right? So we can isolate them each column in the data in 2D NumPy array. So there are other ways you can do this, but here because our goal is now to not to keep these results in NumPy arrays, but to convert them to a data frame. The reason I would like to convert these results into a data frame, because we can easily report, you can record, save it to a file. If you want to save it to an Excel file or CSV file, you can do that very easily using pandas to CSV or to Excel functions. If you wanted to visualize, so visualizing a data frame is much better than a NumPy array, because you can have column names, and the display will be prettier than a NumPy array. You don't need to care about formatting, etc. And also, if you want to do further analysis, having a data frame will be very helpful. Therefore, I wanted to convert my results of the testing data set into a data frame. So this one I do every time. You will see in the notebook. We will be working with machine learning problems. So I'm going to convert the results into a data frame. Okay, so let's see how we can do that. So the function you all know, the constructor for to get a data frame out of the raw data is called pd.dataframe. And you have to provide data as a dictionary. In this case, there are multiple ways you can provide data into a data frame constructor. So here I'm going to provide a dictionary of NumPy arrays. So each NumPy array, I have to provide a column name as the key of that dictionary. For each key, I have a value. That value is the NumPy array. Okay, or we can have list as well, but one condition, all these arrays should be with the same length, or list should be with the same length, right? We have to make sure that. Okay, so the first column is y-actual column, so which contains in the y-test column. The values in y-test column is our y-actual, and y-predicted we predicted above. So here that will be your second column. Y-predicted probability for class 0, y-predicted probability for class 1, you see here, and y-predicted probability for class 2. So those will be your other columns in the result dataset. I call that the new data frame is test results. And let's create that. Okay, first of all, let's execute this line, and then let's execute this line, and then let's see the result data frame. Okay, so let's execute the result data frame. All right, so now you see the result data frame. We created a data frame. I just pulled sample of 10 from the result data frame. We had 30, so 1/3 of your test sample should be here. So y-actual column, y-predicted column, y-probability 0, 1, 2. So we have all the results we wanted to have in this data frame. See how it easy to display it and how to visualize it. So we'll see how a few other uses of it. In any case, if you want to do one-hot encoding your prediction column, there's no obvious reason we do that, but for your understanding, I'm going to do this anyway. We can use the get dummies. It's a function. pd.getDummies is a pandas function, not from your data frame object, but it's from the pandas library. So pd.getDummies, and then you have to provide a series or numpy array, one-dimensional numpy array, or you can use two-dimensional arrays as well, or a data frame you can provide. It will create a dummy variable, set of dummy variables, and then you have to provide prefix. So each dummy variable will be named by the value of it. So we'll see what exactly happening, then we can discuss. So what it does is it will do one-hot encoding. We learned one-hot encoding under feature engineering section. You can go back to that lesson and read more about it, or watch the video if you want. So y-predicted column, you should expect 0, 1, 2 values. So y-predicted, if the value is y-predicted value is 1, your y-pred_1 column is 1, rest of the columns should be 0. Y-pred value is 2, y-pred_2 should be 1, rest of the column should be 0, like that, right? So that's a one-hot encoding you can find here. So this is how you can do that. And but we have no use of this one in this problem, but I just wanted to show you how you need to do this at this point. Okay, so then if you do this one-hot encoding, actually you will the result set will be this. If you want to concatenate or combine, this is another learning for you, how you can combine two data sets together. So this is how you can do that. So if you can use pd.concat, it's another function from pandas library, and then you have to provide one data frame, and the other data frame, you can have multiple data frames, you can provide, all of them will concatenate, and then you have to provide what type of join you will be doing. So because since you are using the row level join, you can provide outer join. You have to provide axis, your axis, you can say axis 1, to say you are joining row levels, or the columns, you are combining combining data set in adding by adding columns, not adding appending rows, but appending columns to your data frame sets, right? The axis 1 will tell the Python what direction it is. All right, so let's we have now the dataset is created, result dataset. So let's try to apply the confusion matrix to evaluate the model. So we will learn about the confusion matrix under model evaluation in a later time, but multiple times I mentioned to you and showed it to you that I'm going to do this anyways. In confusion matrix, we can understand what are the correct predictions and what are the incorrect predictions out of your models, right? So in here, rows in this confusion matrix will tell you what are the actual values and what were the recorded values for this flower, or the known classes for this flower, each and every flower. And columns will indicate the predicted classes for this flower. For example, let's take this cell. So this will tell you the actual value is 0 and also the predicted value is also 0. We had 11 such flower instances in this data set. So predicted correct, right? 0 is the true value or the ground truth, and then predicted as 0. Similarly, 1 predicted as 1 is 8. 2 predicted as 2 is actually 9. Okay, so this diagonal is providing us how many true values or are here, true predicted values. False predicted values are the off diagonal items. You will see this one actually is 2 but predicted as 1, and this one is actually is 1 predicted as true. So those are not correct predictions. Okay, so we can also identify this kind of a thing in a confusion matrix. We will have like a detailed discussion on this in a later time, but for now you can just simply understand what it actually does and what it actually tells you. There are a lot of things. This is a very useful tool in evaluating classification models, the confusion matrix, right? So pay attention to that when we are discussing in our lesson about model evaluation. Another model evaluation metric will be the confusion matrix is not a metric. It's just a matrix. You can get some insights, but the accuracy is a number. You can quantify how good your model is. The accuracy is directly related to confusion matrix. You can derive accuracy from the confusion matrix as well. If you take all diagonal items in the confusion matrix without the total row and column, divided by the total number of observation in your data set. So the 11, 8 and 9. So 8, 9 is 17, 28 divided by 30, right? 28 divided by 30 is your accuracy. So we can do that. So we can say your confusion matrix log 0, 0, 1, 1 and 2, 2. You can get these three values and add them together divided by the value in all. So in this cell. This will give you the accuracy. Let's see what the accuracy tells you. It's telling you the accuracy is 0.93. So 93% accurate. This model is 93% accurate. That's what we can tell. Scikit-learn also provide you a function called accuracy score under metrics. So metrics.accuracy score. Metrics we imported to this notebook earlier in the very first cell. And then metrics.accuracy, you have to provide either numpy array or pandas data frame column or series. So that two columns or like two numpy arrays. The first column or numpy array should tell what is the actual value or the ground truth, and the second column should contain what are the predicted values, which is what it is predicted from your model, right? So once you provided these two columns, it will compute the accuracy score. You don't need to create confusion matrix. So the things will happen within the accuracy score function and it will return the accuracy score. So that should be the same as what you get above, but in a different method. Or I think I recommend the second method, because that's the scikit-learn method is much easier and convenient for you to use. Okay, so there's another metric, F1 score. I'm not going to discuss in detail about F1 score, but I will tell you like few things about the accuracy and F1 score in general. If you want to read more about F1 score, you can go to this link. You can go to scikit-learn and you can search F1 score, and it will show you some pages with details about F1 score. So in very high level, our goal in machine learning model building for classification problem like this, to increase the accuracy. Higher the accuracy is better, but there are some cases against accuracy. I'm going to discuss in our model evaluation section. In some situations, accuracy is not going to be the best metric, so you have to go to other metrics such as F1 score, precision, recall, and some other things we will be going to look at. So F1 score also should be higher. Okay, so in the model building, what our goal is to increase the accuracy, right?
same as the F1 score. The higher F1 score, higher accuracy is your model is better. Lower these values, your model is not performing better. Or you have a room of improvement. You have to work to improve your model accuracy and F1 score, right? So, but here is both having 0.93. If you wanted to further improve to make it 95, 98, 99, yeah, you can go on. So, but you have to work hard to make your variables transformed, and then you have to do more advanced data analysis. You have to be very careful about your analysis and deciding variables, do some feature engineering tasks in order to make this accuracy higher and higher in each step of your model building, right? So, or the F1 score if you want to use that. All right. So that's about the logistic regression classifier. I spent additional time to describe some components about evaluation, confusion metrics, etc., and also identifying model parts or attributes of the model and functions of the model, how we can construct the result table. But in the following part of this notebook, I'm not going to go into very detailed discussions about each and every part. I will discuss only parts relevant to the algorithm or new to this algorithm, which we never covered before, right? Some of the things are repetitive. The same thing we did above, we'll cover again and again with each classifier we are going to evaluate below, right? As I mentioned, scikit-learn use the same set of functions. The fit function is the same function across all the classifiers to train the model. So I don't need to introduce you again and again, right? So pay attention to that. If you have questions, you can let me know anytime. So the decision tree classifier is you all know about decision trees. You can generate a tree if you wanted to make a decision. If you know some conditions, you can say, like, if you wanted to go somewhere. So if you wanted to go somewhere, you say, like, if I can find this amount of money, I will decide to go to this place. If I can collect this amount of money, I will decide to go vacation to this location, right? So then you can have another condition. So if the weather is like rainy, if the weather is snowy, whether the weather is sunny, so then based on that you can make several decisions. So you can make a decision tree if you have like multiple things you need to think before making a final decision. You can have a flow of your decisions in a decision tree. So we all did decision tree at least one point of your education, so you probably know what is decision tree and how you can make decision. This is a very useful tool in some applications, even in modern applications. So we are using decision trees. You can have a decision tree as a diagram posted on the wall, and when you are deciding about something in a, say like in a bank, you wanted to approve or reject a loan, sometimes you have to follow a decision tree, right, to get customer details, and you have to put the customer details to a decision tree, and then you can make some decision, right? That's another example. But in this machine learning, so what the decision tree does is same as the logistic regression. It use like a model fitting, so the equation find out the optimum coefficients and intercept for that logistic regression equation. Here it will find out a tree structure, the optimum tree structure based on the input data or the features and the target variable we provide. It will decide when to split, what conditions to make in order to make a decision in the decision through each node of the decision tree, right? So tree in the computer science, we have nodes or the branches of a tree, and then you have a root, and then each root can have a child nodes, and then each child node can become another parent node, and then may have child nodes, and the tree can go further. So that when you are splitting the tree further, you're saying you are going level, like one level down, and that's called depth, right? So you can say depth is 1, depth is 2. The further you go down, the higher the depth is, right? So number of children, you can think like how many splits I can have in each node. So you can have one node can split into 2 parts, 3 parts, 4 parts, like that. All right, so here to build a decision tree, we previously load the decision tree classifier,
So we are using that as a constructor method, decision tree classifier constructor method, to create model object. So now this model the variable model is storing the model object, decision tree classifier model object. Use random state 0, that's arbitrary, pick a number as a seed. Like I said, the maximum depth I set to 10. So the tree I said I instruct don't go beyond 10 levels down of the root node. And then minimum samples to split. So this is something I can have like another session to describe like how the decision tree is being made in this algorithm. So what it simply does is it will for each node it will keep number of records, right? So belongs to that condition, or belongs to that path. So when it go forward in a path, if you have an samples in that last node or in that path is 2, you can no longer split it. You can split 1 and 1, but here we instruct don't split. You can make it like 5, 10 and a large number. In that case, your tree branching your tree or splitting your nodes further will stop at earlier than you have like a lower number of minimum samples per split, right? So if you have like something like 10 or 20, you will not get like very deep. So when a path comes to a value, the path only contains 20 values, so it will stop from that point. It will not further divide your tree or not create any new child nodes. Okay, so these are some parameters we call like not random state, we call these are hyperparameters. So we will discuss again them in detail with the hyperparameter tuning lesson. But for now, just understand these are some parameters you can provide to tune, or we can instruct your model algorithm, or these are the things that you should consider. Again, like we create the model object and we can train the model, so using the fit function. So since this is a small data set, the training is much faster. It trained your model, and then we can visualize the decision tree. This is why we loaded the tree class or the module earlier. So this tree module has a function called plot tree. So this will help you to plot or visualize the decision tree we created above. So let's see. So this is the visualization of the decision tree. You can see, as I mentioned, it will take this is the decision tree built from the scikit-learn decision tree algorithm. And now you can pass a new flower and the characteristics coming from a new flower. You can pass it through the decision tree and decide and get which class it belongs to. For example, it will do set of condition checks, right? So if the petal width is less than or equal 0.8, if this condition satisfied, it will go to this direction, if not this direction, like that. So it will flow through the branches of the tree, and based on that it will decide if this condition satisfied, if in this first instance, if it went to this direction, this will be the final class, and if it goes through this path, this will be the final class. If it goes through this path, this will be the final class, like that. It will follow. So if the longer path is if it will go to this entire path here, and the longest path is okay. So after checking all these conditions, if it go to this branch, and then this is the final class it's going to give you as the flower belongs to, right? This is how you can visualize a decision tree. If you have like large number of variables, large number of variables, or like you said the depth is very deep, your decision tree could be much larger, so probably you cannot fit into screen, right? But this is a small number of samples, small number of variables for you can easily visualize it. So you can take a look at it and read more about decision trees. I would encourage you to do that, or if you can listen to our lecture about the decision trees in a later time. Okay, so then I'm going to construct the result set, same as I did above. Right, so we have the y actual, y predicted probability, and y predicted probability 1, 2, and the predicted classes one hot encoded at the same column, one hot encoded. Okay, so then let's do the confusion matrix. So nothing new, same as before, and also the result is not different than what we get for logistic regression, right? And let's do the let's do the accuracy and F1 score, and also we see that's not different from what we get above. All right, so now what we can do is we later we are intended to evaluate or like compare the model evaluation. So here I forgot to mention the accuracy. I use the notation accuracy underscore TC. TC stand for tree classifier. Previously I used LGR for logistic regression because I wanted to access these variables in a later time. I'm going to keep the accuracy for each model because that will be helpful for us to compare. So let's do the random forest classifier. So to give you a very high level, what is random forest is random forest classifier use number of trees to build based on your data set, your input features and target variable, and it will build a number of trees as you instructed to build. And in this case the n estimators, the parameter n estimators, will you instruct a random forest algorithm to build 100 trees. You can say build 200, 300, any number of trees depending on the resources available, depending the resources you can allocate into. The higher the trees is, higher the computational resources you need. It will build 100 trees in this case, and then later combine all these and then build 100 trees with different sets of subsamples taken from your original sample, and also subset of columns it will take. So it will take 2 columns at a time in one tree, and another tree it will take 3 columns, another tree it will take all 4 columns, and one tree it will take 100 samples, another tree it will take only 50 samples. Like that it will take subsample of rows and subsample of columns and build number of trees, and then combine the prediction coming from each tree for each record. Say like if you build 100 trees, so for each record you will have 100 different predictions coming from each tree, all 100 trees, right? So each tree will give you one prediction, and then at the end it will combine all these predictions into one and then return you the result. Think like it's like a voting depending on the system you will be using in the algorithm. So it's like a voting, right? So if 60 trees tell you this belongs to class 1, and another 10 tell you belong to class 2, another 30 said class 0. So 60 trees say class 1, that concludes that this record belong to class 1. So in very high level, again we can discuss this in a later time. This is what we do. The name random forest is somewhere you can see many number of trees. So random forest is a tree, and why random? This is like how we randomly pull some subsamples, columns, subset of columns, and etc. So this will randomly make 100 trees and may help you to make this decision. Okay, and here also we can say maximum depth and minimum sample split you can specify for each tree. So even it takes random sampling, but you can specify for every tree. You cannot go beyond 10 levels down. You can split more further than like two records in one node. Okay, so then let's look at the training model. So let's run this, the fit function. So it fit the or train the model random forest classifier, and we do the result set creation and then do the confusion matrix. Here also we don't see any difference in the confusion matrix, and the F1 score and accuracy, they are the same. Okay, if you can take your time, you can pause the video and you can complete this task up to this point. Okay, so once you do this, let's jump to the next model, support vector machines. So we call it like support vector machine. In this classifier we call support vector classifier. So in support vector machine submodel in scikit-learn, so we get the support vector classifier. So you will see the support vector classifier, and we are not going to go into very detail about the classifier itself, but here you can have to provide parameter called a kernel and the parameter c and the return probability from the support vector classifier or not. So you have to provide these to construct the model object. So we say we need probabilities. Okay, and the kernel we use linear kernel. There are a number of kernels. If you want to really read more about it, you have to go to the scikit-learn documentation and read about support vector classifier. We can discuss more in a later time when we are discussing what is support vector classifier in detail. So the train model, and then we get the results. So nothing is going to be different than other two models after this point, right? The scikit-learn use the same API or same set of functions to do the same thing, right? The model predict, medium or predict probability, they are the same. So nothing is changed. And the confusion matrix, we use pandas crosstab to create a confusion matrix. And also I need to mention scikit-learns provide you another function same as the train test split and the accuracy score. You can also create confusion matrix. But I'm not going to use this today. I will be doing this when we are doing model evaluation lesson. But here, like, I'm using the crosstab still. Okay, so we did accuracy and F1 score. Here, one distinction here we found support vector machine or support vector classifier gave us higher accuracy and higher F1 score than other two models, the other three models we looked at. All right. So take your time and you can pause the video and complete this task. And after you do this, let's go to the k-nearest neighbor classifier. So I'm not also going to describe in detail about k-nearest neighbor classifier in this lesson, but you can read more about it in the scikit-learn documentation. So in the k-nearest neighbor classifier, the parameter I'm going to pass is number of neighbors in the k-nearest neighbor classifier. And then that's the only parameter I'm going to pass. Construct the model object, and then use the model fit function, provide your training feature set and the training target variable column. Still we are doing supervised learning, right? I hope you remember. So model is trained, create the result set, no difference than the previous models, right? So, and also the it's very similar to logistic, regression, tree classifier and random forest. So we see only two out of diagonal, and then we see the same accuracy and same precision, so same F1 score. All right, so now we came to the end of this discussion about classifier models. So the model performance, we looked at each and every model. So we looked at accuracy, we looked at F1 score, and we also looked at confusion matrix, but I'm not going to compare confusion matrix for each model, but I'm going to compare accuracy and F1 score for each model. So I'm going to construct a data frame out of these results, right? So for each model, I have the model LGR, it's a logistic regression, what is the accuracy, which holds in this variable, and F1 score. So I'm going to construct this data frame using a dictionary of a list of dictionaries. So each dictionary object will contain evaluation result for a model, right? So this one dictionary object, and then that will contain evaluation result for one model, and list of such dictionaries for each and every model we looked at for all 5 models will make us a data frame. Okay, so I'm going to create that and then I will give some description. Okay, so here we found for each model, or for all 5 models, we found accuracy and F1 score. And here, if you were to pick one model in your project as the winner, or the one you wanted to implement, what would you choose? It's obvious you will take the one with high accuracy and high F1 score. That also need to be like carefully picked, there are other things you need to look at it. So we will discuss about the model evaluation, but in this case you're correct. You can use a support vector classifier model with 0.96 accuracy and 0.96 F1 score. So why this comparison is important? So in a regular machine in a real machine learning problem, if we wanted to if we wanted to build a machine learning model for a real problem, we need to build more than one model. Sometimes we have to build more than one model using the same algorithm. I mentioned to you there are parameters you can set. The parameters change how your algorithm works. For example, minimum depth or the maximum depth or minimum samples to split will change the behavior of your the tree-based classifier. Okay, so by changing that value, you can see what is going to happen to your accuracy and F1 score or any other metric you will be evaluating against the other models, right? So use the same model with different set of hyperparameters. Those are the parameters we used within the model constructor. So we will discuss that in detail. Don't worry if you don't get the concept now, but this multiple models with the same algorithm is possible. But each of these models we need to get the model evaluation results and compare against to find out what is the best model. In some situations we will use multiple models with different algorithms, like in this case for the same problem. So we are trying 2 dimensions. We are changing the same model, multiple different parameters, different hyperparameters, multiple models, could be multiple hyperparameters as well. So that will be like a lot of models you can create. In some situations you have to create 20, sometimes 100 different models and find out which model with which algorithm and which set of hyperparameters will give you the best model. So in this case we are not going to change the hyperparameters. We are not going to do this, but in this case we got to pick the winner is support vector classifier with highest accuracy and highest F1 score. So in a real problem, if you have 100 different models you build, you can automate that process, right? You can write like this into a function. You can let the parameters change automatically, but scikit-learn provide you a method called grid search. You can do some hyperparameter tuning in an automated fashion, and you can make it your life much easier. We will going to discuss that in detail about in the lesson hyperparameter tuning. But now you know what is the importance of model evaluation and what is the importance of how you're comparing models, right? All right, so this is the end of the lesson, and I hope you learned something new out of this lesson today, and we will see you in the next lesson of supervised models for regression, how we can use different type of regression models, and then later we will look into unsupervised models for clustering application. See you in the next lesson.